In your eye, mitochondria sit directly in the path of incoming light. That sounds like a design error, and for a long time it looked like one. Today I want to show you what they're actually doing there, because the answer turns out to be something nobody expected an organelle to do. Let's start with why they're there at all. The cone cells in your retina are the ones responsible for color vision and for fine detail. And they are among the most energy-demanding cells in your entire body. The reason is a process called phototransduction. A photon arrives, hits a light-sensitive molecule, and that triggers a cascade that converts the event into an electrical signal. Then the whole system has to reset, ready for the next photon. That resetting is continuous and expensive, and cones do it constantly in daylight. So each cone needs a lot of ATP, and to supply it, the cell packs a dense bundle of mitochondria into a specific region called the ellipsoid. Now here's the problem. The ellipsoid sits immediately in front of the outer segment, which is the part of the cell that actually detects light. Think about the geometry. Light enters your eye, passes through the retina, and to reach the detector inside a cone it has to travel through that stack of mitochondria first. And mitochondria are not optically simple. They're packed with folded membranes, they're rich in lipids, and they have a different refractive index from the fluid around them. Anything like that in an optical path should scatter light and absorb some fraction of it. So the standard reading was that this is a compromise. The cell needs the energy, the mitochondria have to go somewhere, and they end up in a slightly awkward spot. Some light gets lost, and that's the price. Researchers at the National Eye Institute decided to actually measure it. They worked with cones from ground squirrels. That's a deliberate choice. Ground squirrels are diurnal and their retinas are unusually rich in cones, which makes them a much better model for studying cone optics than a typical rodent. They modified a confocal microscope so they could illuminate the cells from the side and directly observe how light behaved passing through the mitochondrial bundle. Then they backed it up with computational modeling of the electromagnetic physics, using high-resolution reconstructions of real mitochondrial shapes. And what they found is the opposite of a compromise. The mitochondria concentrate the light. Rather than scattering photons away, the tightly packed bundle gathers incoming light and funnels it into a narrow beam, delivered directly into the outer segment behind it. The paper describes the mitochondria alone as sufficient to focus incident light into a thin pencil of light appropriate for detection. Now, when a result is that surprising, the question is how solid the demonstration is. And this is where the study is genuinely lovely. They isolated a layer of these mitochondria-filled structures. Then they took a mask with a slit cut in it, put it in front of a light source, and shone the light through the isolated bundles. At the focal point, an inverted image of the slit appeared. That is precisely what a lens does. A lens produces an inverted real image at its focal point. This isn't lens-like behavior or an analogy. They built the classic optics demonstration and the mitochondria passed it. Their conclusion in the paper is that each mammalian cone photoreceptor may effectively have its own microlens, made of mitochondria. Now, the part that makes this more than a curiosity, there's a phenomenon in vision science called the Stiles-Crawford effect. It's been known for decades and it's well documented. Here's what it is. Light entering your eye through the center of your pupil appears brighter than light of identical intensity entering near the edge of the pupil. Your eye is directionally sensitive. It preferentially responds to light arriving straight on. That's useful. Light coming in at odd angles has usually been scattered somewhere along the way, and ignoring it improves the sharpness of what you see. But the mechanism behind it was never clearly established. These mitochondrial bundles turn out to focus light in an angle-dependent way. Light arriving parallel to the long axis of the cone gets concentrated efficiently. Light arriving off-axis gets concentrated much less. And the angular dependence they measured quantitatively matches the Stiles-Crawford effect. So a long-standing puzzle in human vision may come down to the optical properties of organelles that everybody classified as power plants. There's a further detail I find satisfying. The researchers tested whether the arrangement matters by simulating alternatives. Elongated, tightly packed mitochondria concentrated light better than the same volume arranged as roughly spherical ones. The shape isn't incidental, and they noted that a single giant mitochondrion would be an especially effective focusing structure, which is interesting because some species do exactly that. Certain tree shrew and zebrafish cones contain giant mitochondria, and other species have structures called ellipsosomes in the same position. different animals converging on the same optical solution. Now let me give you the honest limits because there are a few. This was done in ground squirrel cones. Excellent model, cone-rich retina, but not a human eye. The findings combine direct imaging with computational simulation. The simulations are grounded in real reconstructed mitochondrial shapes, which is the right way to do it, but part of the conclusion rests on modeling rather than direct measurement. And the paper is careful about scope. It establishes an optical role. It doesn't claim mitochondria evolved primarily as lenses, and neither will I. The energy demand of cones is enormous and real. What the work shows is that a structure clearly built for one purpose is also performing another. So what do you do with this? Nothing. There's no protocol, no intervention, nothing to adjust. This is anatomy and physics. What I'd offer instead is a change in how you picture the thing. We call mitochondria the powerhouse of the cell, and that phrase has done a lot of damage to how people think. It implies one job: generate energy, hand it off, that's the whole story. Over the last few weeks on this channel, I've covered mitochondria that dock onto the nucleus to deliver energy directly, that form a conducting network across a muscle cell, that sense heme availability, that signal cell death, and that get deliberately destroyed as part of normal development. And now this. In your eye, they're optical hardware. Powerhouse is not wrong. It's just about a tenth of the description. Now where my own recommendation sits, and today it's narrow as ever. CoQ10 is a carrier in the electron transport chain, and cone photoreceptors run that chain hard, because phototransduction is expensive. Levels tend to decline as we age. That's a claim about energy production. It has nothing to do with the optical properties described in this study. Nobody has looked at that, and I'm not going to imply a connection. The link in the description below goes to a free 5-item morning checklist. Mitolenses on that page too, and it's an affiliate link. I earn a commission at no extra cost to you. And if you want more of this, subscribe. This video is educational only, and it's not medical advice.